Hey, welcome back. So this is Introduction to Differential Equations in Calc 2. And we'll begin with just a definition of what the heck these things are and some examples and that sort of thing. So first off, a differential equation. What the heck is this thing? So recall back in the day, you may have had to solve something like 2x plus 3 equals 5. And what you'd be looking for is a number such that when you substitute it in there, it satisfies the equation, right? So we had methods. You could subtract 3 from both sides, divide by 2. Ultimately, you get x equals 1, right? Now, instead of looking for a number, we're looking for a function that satisfies a particular equation. So like y prime plus 2y equals 0. It will turn out that the solution is y equals ce to the negative 2x. Okay? So a little bit different, and we're going to have to develop some tools for doing this. In general, these differential equations get very, very complicated, and they won't always have methods that you could just pick out of your toolbox and go at it and find the answer. So you're going to have to, along the way, also develop these other methods, these analytical methods. And here we'll see slope fields and Eulers Method that will allow you to get solutions, even though you can't get the solutions via some sort of algorithmic kind of application. Okay, so hopefully that, differential equations are nothing new. You've seen differential equations before. Anytime you find the antiderivative of something like this, y prime equals 2x, the solution of, and this is a differential equation, the solution of that is basically just integrating, right? So if you took the integral of 2x dx, you would get 2x squared over 2 plus c. And of course, that would just be x squared plus c. This thing would be called the general solution to that differential equation. So in the homework, you're going to see a lot of these kind of just integral problems, basically what they'll come down to. Yeah, so down here, you see like the integral of 5 tan squared. Let's try one of those, right? So number 10 in WebAssign, you get dy over dx is 5 tan squared x. So technically it is a differential equation. It's not a very hard differential equation because you pretty much already have the method for solving it. You're just going to integrate. So the solution will be the integral of 5 tan squared x dx. Of course, we're going to need some identities to pull this off, right? So remember the fundamental sine squared x plus cosine squared x is 1. Divide through by cosine squared, you get tan squared x plus 1 is secant squared x. Then you could solve for tan squared x, secant squared x minus 1. And then we could do a substitution on that. Let's go ahead and factor out the 5. Secant squared x minus 1 dx. So we end up with 5. Integral of secant squared is tan x. Integral of 1 is just x, and then plus or constant. So this would be 5 tan x minus 5x plus c. And that would be our, what they call general solution. Whenever you see that plus c, that's a general solution. So let's make sure it works. Minus 5x, and better use that capital C, right? Okay. Okay, so if you know how to integrate, you know how to solve a certain class of differential equations right off the bat. Okay, we are going to obviously be looking at more and more complicated differential equations and classifying some of them. One way to classify a differential equation is just by the order. So to order of the differential equation. And up to this point, you've not really seen a lot of differential equations. You probably have seen like the position equation, which we can get by integrating the acceleration equation in physics, right? So that particular differential equation had order 2, and you see it over here in the book, S double prime. The acceleration is equal to negative 32. That is a second order differential equation because the highest ordered derivative that you see in the differential equation is 2, second derivative. Okay, so the order here, or we could just say second order differential equation. Okay, so that would be one example. Another example, and these things after a while they kind of look like polynomials, and that would be a certain class of differential equation you would study. 9 plus y equals e to the x, something like this. Again, this is the highest order derivative here is that 3. So this has a third order differential equation. Okay. When we integrated back here in this example, we got this general solution x squared plus c, and then this example, these were both first order differential equations. But if you're working with a second order differential equation or a third order differential equation, instead of having just one plus c, you'll have multiple c's. Okay? You'll have a c1, c2, all the way up to the order of the differential equation. So a second order differential equation, the general solution would have 2 constants. For a third order differential equation, your general solution would have 3 constants. And in order to get the what they're going to call particular solutions, you're going to need initial conditions. And then you have to use the initial conditions to solve for these particular constants. Okay? Before we get to that, let's go ahead and just work with checking whether or not a solution works. Okay, so I guess I'll put this as 3 checking solutions. So you've done this before with your work in just regular algebra here. So maybe you're given an equation 2x plus 3 is 5, and this would have been before you actually knew how to solve the equation. And then they would say, is x equal 1 a solution? So what did you do? You could basically put the 1 into this equation, and then simplify, and you hope you get 5, right? You want to start on one side and then hopefully connect it to the other side somehow. So 2 plus 1 is 2 plus 3, and then 2 plus 3 is 5. And that pretty much proves that it's a solution to that equation, okay? So now what we want to do is kind of the same thing, except instead of having this number that we're checking a function, okay? So now let's go ahead and look at example 1 in the book. Okay, so we're given a differential equation. I'll set it up just like they used to set up the old algebra questions. So we want to see if y equals sine x is a solution. It's not a matter of just substituting in. You kind of have to leech off of the given solution and get the derivatives that you need in order to substitute it into the equation. Okay, so you're allowed to work with the solution here that's given and find derivatives or manipulate it in any way you want. So that becomes your kind of given information. Okay, so y is sine x. Y prime from calculus is cosine x, and then y double prime is going to be negative sine x. Okay, and we could use that, do substitutions in order to get from one side of the equation to the other. Okay. Usually the book doesn't, but I usually tell the reader which side I'm starting on. So starting on the left-hand side, I note y double prime minus y, and then I start using the stuff in the box here, this given kind of information, and I hope to get over to 0. If you can't, then it's not a solution, okay? So we got negative sine x minus y, which is sine x, which is equal to negative 2 sine x, and that's definitely, I mean, when x is equal to 0, it works, but for all x's, it does not work. And it would need to work for all x's, okay? So this is not a solution. You could easily remedy that differential equation by just saying y double prime plus y equals 0, and then I think it would be a solution. Okay. Let's move on now to part B. Y double prime minus y equals 0, and we want to know if y equals 4e to the negative x solution. Okay. So again, I'm going to get the second derivative first off. So the derivative of 4e to the negative x is 4e to the negative x times the derivative of the exponent, which is negative 1. Let's rewrite that. Negative 4e to the negative x. That was y prime. Y double prime is then going to be negative 4e to the negative x times, again, negative 1, the chain rule. That's positive 4e to negative x. Okay, so this is my given information. Okay. Again, I'm going to tell the reader which side I'm starting on. So starting on the left-hand side, I notice y double prime minus y equals, and now I do substitution, so 4e to the negative x, and then minus y, which is 4e to the negative x. And of course, that equals 0, which is the right-hand side, which proves it's a solution. Okay, so that one works. Part C, again, I'll rewrite the differential equation. And my potential solution here, y equals ce to the x. Okay. So one thing to note in part B, this thing that doesn't have a c in it, they're going to call that a particular solution. Oops. And if it does have a c in it, then it's a general solution. So this is more of a general solution. Okay, let's see if it works. So I'm going to have to generate my derivatives. So y prime is ce to the x. Oh, it's always just ce to the x. Okay, great. All right, so again, starting on the left-hand side, I note y double prime minus y equals. So y double prime is ce to the x, then minus y is ce to the x. So that one works as well, right? So that is a solution. I really wouldn't want to say that that's the general solution because you should be able to get all the other solutions from the general solution. And if you look back at part B, that is a solution, but we couldn't obtain it necessarily from this solution in part C. When you can't obtain a solution from the general solution, it's called a singular solution, but in particular here, I don't think this is the general solution anyways. So I think I misspoke when I said just because you see a C, it's a general solution. That's not necessarily the case. Okay, so I don't know. Let's kind of move on. So now that they're talking more about general solutions in the book. Well, before I get there, let me just look at one example where you're trying to prove it's a solution, but it's a little bit more complicated. So the notes aren't really giving you hardcore examples. I just want one that's a little more hardcore. So here's a differential equation, 2xy all over x squared minus y squared. And then we have this is a general solution, x squared plus y squared equals cy. Okay, so I'm gonna, I need the first derivative here, and worse than that, moreover, in order to get from the left side to the right side, I'm probably going to have to solve for c eventually, and so I'm going to work completely with this x squared plus y squared cy at first. I need the derivative y prime, and in order to get sort of the derivative, I have to do implicit differentiation in this case. So the derivative of x squared is 2x. The derivative of y squared is going to be 2y. Then you always have to tack on a y prime, right, when you're taking the derivative with respect to, when you're taking the derivative of the y, the dependent variable. Okay, so on the other side then I have c times the derivative of y is 1 times y prime. And then I'm going to solve for y prime. Okay, so I'm going to collect the y prime stuff on one side. I get 2i y prime minus cy prime equals negative 2x. Factor out the y prime. 2y minus c equals negative 2x. Divide. Prime is negative 2x all over 2y minus c. And now I'm gonna try to see if I can connect the right-hand side of the equation to the left-hand side of the equation. You're going to see it's not going to quite work, right? So starting on the left-hand side, I note y prime is equal to negative 2x all over 2y minus c. So the problem between the right-hand side here and this thing right here is this c part right here. I need to get rid of that c in order to connect the two sides of the equation. So what I'm going to do is go back to my sort of given information here in this box and use this equation to solve for c. Okay, and I'm allowed to do that. So I'm going to divide both sides by y, and I just get c equals x squared plus y squared all over y. And then I'm going to take that and dump it into my differential equation down here and see if that will kind of get me to the right-hand side. Okay, so let's do that. This will be negative 2x all over 2y minus x squared plus y squared all over y. Not a fan of complex fractions, so I'm going to multiply top and bottom by y. Okay. So we'll have negative 2xy all over, I'm going to have to distribute here, 2y squared minus x squared plus y squared, and then I'm going to go negative 2xy all over 2y squared minus x squared minus y squared, and then I'll be negative 2xy all over, what do we get, y squared minus x squared. So am I getting close? Yeah. And then I could factor the negative out of the top and put it in the bottom. So I'll have 2xy. I mean, you can literally do it one step at a time if you're kind of worried about this operation. Put the negative downstairs. Just slowly moved it downstairs. And then I got 2xy. Distribute the negative, you'll end up with x squared minus y squared, which is the right-hand side of the differential equation. And that shows it's a solution. So okay, so I just wanted to show you one that was a little bit more complicated than the other ones. Okay, so back over here at the book, they start talking about solution curves, and that's what happens when you graph this general solution thing. You're not just dealing with one curve, you're dealing with a bunch of curves. And for each value of c that you choose, you get a different solution curve. And in general, they'll give you what are called initial conditions. Okay, so you'll solve the differential equation, you'll get a general solution, and then using the initial conditions, you could solve for those constants c. All right. So in particular, in their example here, I don't think they really give this a number. They are doing that position equation from physics. So I'll just say example from the book here. They have S of t equals negative 16t squared plus c1t plus c2. This is the general solution. But in physics problems, they'll generally give you like the initial position. So the position at time 0 is maybe like 80 feet, like maybe you're standing on top of a building. Then they'll tell you a velocity. So maybe you're up there and you're going to throw a baseball at 64 miles per hour. Then you could use these two initial conditions to solve out for the constants C1 and C2 and obtain a particular solution. Okay, so how do I find then particular solutions given these initial conditions? So that will go and take us to here, example 2. They're giving us a differential equation, and they're saying to verify that y equals cx cubed is a solution, and we're going to assume that x is greater than 0. Okay, so first I'm going to verify it's a solution, and then they also give you initial conditions 3, 2. So x is 3, y is 2. So that will allow us to get a particular solution. So this we're assuming is some sort of general solution. They want a particular solution without the c. Okay, so let's verify it works. So first off, I have to kind of get that derivative thing again. So I get doing a power rule, 3c x squared for the derivative. And then starting on the left-hand side, xy prime minus 3y is going to be x times 3cx squared minus 3 times cx cubed. And of course, that'll be 3cx cubed minus 3cx cubed. Whoops, and I forgot to write in the other side of the differential equation. And then that'll equal 0, which proves it's a solution. So it's a solution. Okay. Now we want to get a particular solution given this initial condition, which they've thrown in our lap here. Okay. So again, my general solution, y equals, let's go back to black, y equals cx cubed, and then my initial condition 3, 2. Okay. It's pretty easy. All you got to do is sub in these numbers for x and y, and then solve for c. So you get 2 equals c times 3 cubed. 3 times 3 is 9 times 3 is 27. So c equals 2 all over 27, and then you just sub it back into the original, the general solution there. So the particular solution, y equals 2 over 27 x cubed. Okay, and that's for x greater than 0. Okay, and then they show that particular solution, and all is well. Okay. Like I said before, sometimes you're just not going to be able to solve these differential equations. The only technique we have right now is integration, and as you probably look at these equations, integration just isn't going to cut it to, for example, example 2, you're not going to be able to do that via integration. You're not going to be able to solve that thing. So one technique you can use instead is generating a slope field, and then that will allow you to kind of see what your solution looks like. Okay, so section 2, slope fields. And it is a time-consuming effort. Back in my day, before we had calculators that could do this, I would sit around filling notebooks with this kind of stuff, and it was quite a worthless endeavor at this point. So, but we all have to jump hurdles in our lives. Anyways, what is a slope field? It's the graph of it's basically a bunch of little, looks like a bunch of tick marks. So let's see if we can find, yeah, these things. These things are slope fields. And what they are the graphs of slopes of solution curves. So, and you know, back here you would have, well, back here on this other page, you would have a family of solutions, okay, like here. Imagine putting little slope marks all over this, okay? That would give you a slope field, and that's what you're going to see over here. For us, we're not going to be able to generate a slope field unless you have a particular form for a differential equation, so you need this kind of form, dy over dx equals some function of x and y. Okay. Let's look at example 3 and get a slope field for, well, actually, maybe even better than example 3. Let me do one of my impromptu examples. So the example we know a solution to, y prime equals 2x, right? We know the solution to that is x squared plus c. Okay, so a slope field, all we're doing is working with this equation, and we're going to do kind of a t-table, and we're going to just do a bunch of points around 0, 0. Okay, so here's 0, 0, and I'm going to do like 9 points. So this may be a little time consuming, but okay. So negative 1, negative 1, negative 1, 0, negative 1, 1, 0, negative 1, 0, 0, 0, 1, 1, negative 1, 1, 0, 1, 1. Okay. And we're going to put these ordered pairs into this differential equation here. Usually, I mean, sometimes, like in the example here, the differential equation has an x and a y in it. This is y prime is x minus y. In my example, I only have the x coordinate, so it's only dependent on the x. And so it's a little easier than most of them. So anyways, plugging negative 1 in into 2x, you get negative 2. So negative 2, negative 2. Plugging 0 in, you get 0. Plugging 1 in, you get 2. Okay. All right, so down here in the graph, wherever I see one of these points, I'm going to put a little tick mark to represent a slope. Okay. So first at negative 1 down here, I'm going to put a little tick mark that has slope negative 2. So down 1, 2 over 1, and it looks something like that, right? Negative 1, 0, again, I have the slope mark like that, and then also at negative 1, 1. In the middle here, they're all 0, so 0 slope is just a horizontal. And then at when x is 1, all the slopes are 2. So up 2 over 1, and you get this thing. Okay. So what? Well, for any particular initial value you pick, so let's say my initial value is like 1/2 right here. You can kind of follow the tick marks, and they will give you kind of a good description of the solution, what the solution would look like. So it kind of creates a little maze, and if you just draw through the maze, you get kind of a solution, what the solution looks like. And sure enough, that's what our solutions look like, right? Because our solutions are all parabolas. Okay, so it's a cheap way to produce kind of a graphical, a picture of what your solution is. And that's all they're doing. And it is time consuming, so you're probably not going to want to do many of these by hand. I think most of the ones in the homework are just, match up, or yeah, worst case, they do have you kind of go through. So like number 12, we can do that real quick. The differential equation is dy over dx equals x minus y. So at every point they give you negative 4, 6, you're plugging it into this thing. So the first one, negative 4 minus 6 would be negative 10. And then the negative 2 minus 2 would be negative 4. And then 0 minus 6 is negative 6. 2 minus 2 is 0. 4 minus 6, negative 2. 8 minus 8 is 0 again. And then you can look at the graph and kind of see, yeah, at when x is 0, when x is 0 and y is 6, you have a slope going down, negative 6. At 2, 2, you should have a horizontal slope, and you can kind of see it there on the graph. Yeah. And then if you wanted to, you could kind of sketch in a solution and see what it looks like. So it's kind of like a parabola with a weird slant asymptote right here. Okay. So you're just guessing. Okay, so that's all very interesting. That's one kind of cheap method you have to produce a solution if you don't know how to get the solution. Another way to get solutions is this thing called Eulers Method. And yeah, I'm not mispronouncing that. It's pronounced Euler. And the Euler method is more of like a computer method, like a numerical method for getting solutions. And the idea is you kind of have a set change in x, which they're going to call h, and then you have your differential equation, which will be, some function of x and y. And what you're doing is using the differential equation. So you're going to have an initial value, so maybe like right here. You'll plop that initial value into the differential equation, and it'll give you one of those little slope marks like we were just producing. Then you use that slope mark to go from the first x value to the second x value, and that distance is fixed, right? That's that h distance. Okay, so you're going to use that slope mark to go from here to here. That'll give you a new point right here. And then you take that point and you put it into the differential equation, and that'll give you a new slope direction, okay? A new tick mark. And then you just use that. It's kind of like, I used to say it's like Spider-Man shooting a web, and then he goes from house to house. It works a lot like that. So you use that as your new web. And of course, you're going over again by h to this new h value. And then that'll be your new place, your new building. And then you go back to the differential equation, you get a new slope mark, and then use that. And basically what you end up with is maybe your real solution would look like this. This will give you kind of a polygonal approximation to the regular solution. And the book does a little better picture, more justice to the picture than I can do. So you can kind of see, yeah, so you can see they're kind of using the Spider-Man method, and you get this kind of polygonal approximation to the exact solution. Okay. So how does this method work? It's an iterative method, so you'll start with some initial value, x0, y0. They're going to tell you the number of steps that they want you to use, which is going to be n. So the number of steps. Of course, you'll have your differential equation, dy over dx equals some big f of xy. They'll tell you your change in x. What the heck is this? So you'll have some h, or change in x if you want. And then the formula for generating the next y value. So the x values formula is just the previous x plus the h value. The y formula, what you do is take the previous y height, and then you add in the change in y that you get from the differential equation. So to get the change in y, you just multiply the derivative times the change in x, right? Because you change in x times the derivative, the change in x is kind of cross out, and then you're just left with the change in y. And of course, they don't use dy over dx, they just use this f of x sub n. minus 1, comma y sub n minus 1. The previous point plugged into the differential equation. Okay. Okay, it's an iterative method, and again, it is time consuming. Let's look at, I guess, this one in the book, and they want us to use Eulers method to approximate a particular solution of the differential equation passing through 0, 1, use a step of h equal 0.1, and then they want you to create a table, n equals 10. Okay. So we'll do one by hand, and then I'll just go to the computer and show you how to do them online. So anyways, example 6. Our differential equation y prime is x minus y. So that's what they're calling the f of xy. The initial value is 0, 1. They want 10 steps, and they want the h value, which is our change in x, to be 0.1. Okay. Okay, so here we go. I'm going to get my calculator and Maple, no, math, what the heck is that thing called? Wolfram. And I could kind of go in there and hopefully iterate this thing out. Okay, so anyways, you could do it as a table if you want. So you have your x sub 0. I'm going to do it longhand, y sub 0. And the x part doesn't really need a lot of room, so y sub 0. So x is starting at 0, y sub 0 starting at 1, and then x sub 1 will be 0 plus 0.1, so 0.1. And then y sub 1 is going to be the previous y, so y sub 0 is 1, plus h, which is 0.1, times f of x evaluated at the previous point. So I'm going to put 0, 1 into x minus y. So I get 0 minus 1. Okay. And then I could just plug this, 1 minus 0.1 is 0.9. Okay. So that should be my y1. And it is. Then x sub 2, you just add 0.1 into the mix there. So I get y sub 2 is the previous y, 0.9, plus h, 0.1, times the previous x is 0.1, minus the previous y, 0.9. Okay. And I'm going to start going to my calculator, not because I can't do it, it's just because I've learned not to trust myself. 0.82. X sub 3, 0.3, y sub 3, 0.82 plus 0.1 times 0.2 minus 0.82. I just want to make sure I'm on target. Yeah. Okay, and I think we can just go in here and edit these on 8.2. 8.2, and this one's 0.2. So 0.758. Okay. So x4, x5, x6, x7, x8, x9, 10, and it is, time consuming. Okay. Okay, I'm going to pause the video and kind of do all the work. Okay, you could pause the video too and see if you can fill out the table. Okay, so magically in 1 second, the whole answer is going to pop up. Okay, so you might want to see if you can do it on your own. It's good practice to at least do it once by hand. Okay, so I'm going to pause the video. Okay, so there it is in all of its glory. And the book is nice enough to kind of give you an approximate solution and show you what it looks like. Okay, great. Let's look at, so online, I would recommend doing this online for the future. You can go ahead and do this one. So y prime is, and this is it's on Planet Calc. So just Google Planet Calc online Euler Method calculator. This one works pretty good. So anyways, y prime is x minus y. The initial x is 0, the initial y is 1. I want, the point approximation is kind of where I'm going to, so I want x equals 1. That'll give me the 10 if I use 0.1 as. I don't need an exact solution if you don't know it. And then you can calculate it, and it should give you, it's rounding, unfortunately. But I don't know if it can give you better. Oh yeah, it can give you better precision. Oh yeah, so they get my answer there. Okay. So you should be able to, in the homework, I think there's only one of those problems, and you can just use the Euler calculator if you want to. I'm never going to know. I'm not going to put it on the test either, because I don't expect you to take 20 minutes on a hour and a half long test just to do one question. That would be insane, at least at this level. So anyways, there's that. I didn't give you the quiz yet, so let me give you the video quiz for the day. Let's make it one of these exercises. Oh, let's make it number 11. That'll be annoying. So this is the video quiz. All they're doing is making you solve this differential equation using integration. Okay, so I like this problem because this is one of those ones where the u sub doesn't quite do it, doesn't quite cut the mustard. So anyways, y will equal the integral of that thing. And you could try to do a u sub on the x minus 18, but you kind of not be able to get rid of that x in front. du is just dx. So what you want to do, again, is take this equation and solve it for x. Okay, so x would equal u plus 18. And then you could go ahead and rock and roll, right? So replace x with u plus 18. Then you have the square root of u, or let's write it as u to the 1/2, right? And then you have dx, which is just du, and then you have to distribute. So the integral of u to the 2/2 plus 1/2 is 3/2 plus 18 u to the 1/2 du. So then power rule, u to the 3/2 plus 2/2 is 5/2. Divided by 5/2, same as multiplying by the reciprocal, 2/5, plus 18 u to the 3/2 times the reciprocal, 2/3, plus your constant. And that would be back subbing x minus 18 to the 5/2 plus 3 goes in 18 6 times, 12 times x minus 18 to the 3/2 plus c, and that should get the job done. Okay. Let's make sure it works, so I'm not misleading another generation of young calc students. Hey, my cat just bit me, sorry. It's getting older. Halves plus 12 x minus 18. Oops. No. Raised to the 3/2. And plus big C. Yay. Alright, I think that should do it. If you're just checking solutions, get a particular solution. Okay, yeah, okay, so maybe this one. You guys want to see this one? Sure, let's do number 6. And then I'll call it quits. Verify the general solution satisfies the equation, then find the particular solution. I mean, honestly, you don't have to verify the thing works for this problem. Clearly, it's not going to know if you verify or not. It's good practice. I'm not going to do it, though. the initial conditions, there's 2 of them. And then y prime is 13, x is pi over 6. Okay, so usually what happens is you end up with a system of equations. This one may be too easy. Too easy. Well. Okay, yeah, this one's too easy. Oh, man, really? Sorry. I'll do it anyways. Okay, so I need the derivative. Y prime is going to be, chain rule on it. So 3c1 cosine 3x plus 3c2 negative. So minus 3c2 cosine sine 3x. Ugh. Great. So no doubt I'll screw that up if I don't rewrite it. Sorry. So yeah, 3c1 cosine 3x minus 3c2 sine 3x. Okay, so I'm putting these initial conditions into that guy. So I get 11 equals c1 sine 3 times pi over 6 is pi over 2 plus c2 cosine 3 times pi over 6 is pi over 2. So sine of pi over 2 is 1, so c1. So cosine of pi over 2 is 0, so you just automatically get c1 is 11. Then I'm going to take this junk and plop it into there, so I get 13 equals 3c1 cosine of pi over 2 minus 3c2 sine of pi over 2. And again, cosine of pi over 2 is 0, so you just get negative 3c2 times sine of pi over 2 is 1. Ugh, so c2 is negative 13 thirds. And then you just plop those two coefficients back into your general solution. And that's your answer. So y is 11 sine 3x minus 13 thirds cosine of 3x. Let's see if that works. 11 sine 3x minus 13 thirds cosine of 3x. Yay! Okay, we'll leave it at that. As usual, thank you for watching, and we'll see you next time.